So you're restricted in terms of how much data you can store. If you go to a 64-bit operating system, obviously it's only the physical memory on the server which is pretty much going to restrict you. Even so, you're still restricted by the amount of physical memory on a particular server, because all the data has to fit on every single server. And secondly, if you're using Java and you have a very large heap, then you do run into garbage collection problems. So although you could theoretically have a 50 gigabyte heap, you don't tend to want to have that. So again, you know, a replicated cache is restricting. It just doesn't scale for larger volumes of data. It also doesn't work very well if your data changes frequently, because every change has to be sent to every Java program in the cluster. Now, if you have a large cluster of 100 JVMs, or even a relatively small cluster of 10 JVMs, every time you change a piece of data, you have to tell every other JVM in the cluster that that data has changed. Caches like EHcache, one of the open source caching technologies, use a replicated cache. They call it a distributed cache, but it just means distributing the same data everywhere. So for very simplistic caching strategies, a replicated cache is fine, especially if the data doesn't change too often. But it doesn't scale, and it doesn't work for data that changes a lot. Partition cache is, as you would expect, basically the data in a lookup table is chopped up and spread about. So every JVM in the cluster, so if you have 10 JVMs and a lookup table with 10 gigabytes of data in it, each JVM in the cluster would have 1 gigabyte worth of data. And if you start up more Java programs in the cluster, so you increase your cluster size to 20 JVMs, each of them would have 500 megs. So the more JVMs there are, the more diluted the data is. The benefit of that is your cache or your lookup table can be pretty much as big as you like. You know, I've started up clusters with nearly a terabyte of data actually held in memory across all the JVMs. So you can have very, very large lookup tables. The other thing is, because in a partition cache there is only one copy of any piece of data, because you've effectively segmented or partitioned your data, any changes only has to happen in one place. You go to where the data is, you modify it, and that's it. There is a replica kept somewhere else if you need the data to be resilient, but there will only typically be one other copy. So it's deterministic. It doesn't matter how big your cache is. You know how long it's going to take to update your data. Whereas with a replicated cache, that's not true. A near cache is a sort of hybrid lookup table. If I'm a client and I want to access information in a cache, typically you're going across the network to get that data. On a gig Ethernet connection, you're typically going to take you for, say, a 20K object. It's going to take you about half a millisecond to read that information across the network. And most of that time, 95% of that time, is spent on the network. So if I'm a client and I'm on a gig Ethernet connection and I'm going to get a piece of data out of the cache, that half a millisecond, if you break it down into where the time is spent, you're probably talking about 20 microseconds to actually look the data up in the JVM, and the rest of the time is actually spent making the request and sending the data back across the network. Now, if you do that more than once and the data doesn't change, what you can do is you can create a near cache on the client. So you create a little local cache on the client. So if I'm a client and I request a piece of data and it comes back across the network, I can keep a local copy. So next time I need it, I just look in my local cache. I don't need to go across the network, so the response is instantaneous. The clever thing about a near cache is that if someone else, another client, changes that piece of data in the Coherence cache, then Coherence will tell all the clients that have local copies in their near cache of that data that it's now changed. So to either throw away the copy that they have because it's now stale, or give them the latest copy. So it keeps all the local copies that clients have, which they use to improve performance, up to date. So that's what a near cache is, and these are the different caching strategies you can use with Coherence. Just to illustrate how this works, in this diagram you can see we're doing a sort of GET request, which is a read from a map. Now in the top left-hand side you can see JVM1, which is being the client here. As far as it's concerned, all the data items A, B, C, and D are all local. It doesn't know where they are on the network. but there are actually 4 JVMs running here holding the data. We're using a partition cache strategy here, so the data is being split up and spread around. And you'll notice that there's a backup and a primary copy of each piece of data. The reason we do that is for resilience. So if a process dies and it has a piece of data in, then we keep 2 copies of it, and 1 copy will be in another JVM to ensure that we don't lose any data. So here you'll see on JVM 1 you'll see a primary copy of data item A, and on JVM 4 in the bottom right hand side you'll see a backup copy of data item A. So when the client's requesting a piece of data A, it's fine, it's local within the JVM. When it requests data item B, it's pulled seamlessly across the network to the client from JVM 2. So the client doesn't see where the data comes from, it just requests the data and it all seems local. To change data on the network or change data in a cache, again the client thinks all the data is local, but when it changes data item A, there's a synchronous update done against data item A, or the backup of data item A on JVM 4. So Coherence doesn't allow you to do this asynchronously, and again that differs from some other vendors' products. When you change a piece of data, the primary and the backup copy are changed in a synchronous operation, so they can't come out of sync. So you guarantee that your data is safe once you've changed it because you have 2 copies. You can have as many backup copies as you like, but typically 95%, in fact, we don't know of anybody in production who's having more than 1 backup. And the problem with that is if you have more than 1 backup, you start to go down the route of a replicated cache where you have the issues. If I change a piece of data, I've got to update it in lots of separate places. Typically 1 backup is sufficient to ensure the data is safe. So inevitably things go wrong. So what happens when one of the JVM dies? Processes die for whatever reason. There could be a bug in the JVM. Your application could have a bug. Someone could just kill the process by accident. The server that JVM's on, because these JVMs could be on physically different servers, could be shut down or just fail for some reason. So here we have JVM 2 dying. So what happens when that dies? Well, the primary copy of B was on that JVM, but the backup was on JVM 3. So what Coherence does behind the scenes, and this is transparent to the client doesn't have to worry about this. And if it's requesting a piece of data which was on a failed JVM, so if in this case the client is requesting data item B, but data item B, or the primary copy, is gone now because the JVM it was on has died. Coherence acts as a traffic cop, and requests for information which is being recovered or moved around is just held up momentarily while it reorganizes the data to ensure it's safe again. So at the bottom of your screen on JVM 3, the backup copy of data item B is promoted to a primary and creates a new backup on JVM 4. And the same thing's true with the backup of data item D. That's been lost. So what happens is that on JVM 4, the primary copy of data item D creates a new backup on JVM 3. So this sort of recovery takes place completely transparently to the client. And this is one of the clever things really about Coherence. It takes care of failure for you. I think I've pretty much covered a near scheme actually, how sometimes a type of cache or lookup table is called a scheme in Coherence terms. But some things to mention which I haven't covered are that if you have a local cache on your client, you obviously don't want that cache to be too big because it's usually a desktop PC or something like that. So you can configure an eviction strategy. That means that you size limit your cache so that your local cache on your client, so it doesn't get too big, and you just throw away the oldest copies of data which aren't being used. And it's very easy to specify in a configuration file on your client, what type of strategies you want to use, and typically use like the least frequently used or least recently used eviction algorithm. So